And you see that here you get, from this you get n squared, k squared, and it will cancel, and you'll get an upper bound on C, or in other words, a lower bound on R, which, believe me, will come out to be exactly this. Okay, so it's a simple calculation. So this is how you get a lower bound if all the non-zero entries were ones. Okay, because they are bounded, and you can do this calculation. You know what the inner products are exactly. Okay, everybody is okay with this. Okay. So what do you do if not? Now it's more simple. Well, if it's not, you reduce to it, and the reduction uses this amazing idea of matrix scaling. How many people have never seen matrix scaling in action? Okay, great, because you are into some fun. It's something that was introduced by Synchron. And the question there, so I'm not sure that I'll eventually get to show you how it applies to our problem, but I'll tell you about scaling. And at least you can see, you'll believe that you can take arbitrary matrices and put them, control their entries, bring them into other matrices that have controlled bounded entries and satisfy all sorts of properties. So let me tell you about the original problem that this was applied to. In some sense, our problem is similar. It's only a rectangular version of a square problem, and it's an L2 version of an L1 problem. So you have to make some changes, but the same idea applies. So let me tell you about the original idea of matrix scaling. So, okay, so the question is the following. I give you an arbitrary matrix, which is non-negative. So maybe we should call it, maybe it's M, or let's call it something else, B. So suppose that B is an n-byte matrix. And suppose it's non-negative, so Bij. This is certainly not our situation, but in our situation we'll just have to square the entries, and then they become non-negative. It's non-negative, and you would like it to be doubly stochastic. So you would like it to have the row sums and column sum 1. Okay. And what you're allowed to do to achieve this is simply multiply, so scale, I should say scale the rows. You can multiply the rows by arbitrary constants, and you can multiply the columns by arbitrary constants. So what you want, if you think of X as a diagonal matrix, Xn, and Y the diagonal matrix, Yn, what you want is that X, B, Y, this new matrix, will be doubly stochastic. Which is a fancy name for saying that row sums is the same as the column sums. Every row sum and every column sum, every row sum and every column sum is 1. Okay? It's like a matrix of a Markov chain, which is the matrix and its reverse are Markov chain. So that's a doubly stochastic matrix. So can you do it? For which matrices can you do it? Can you do it for every matrix? Well, certainly you can't do it for every matrix. What's an example of a matrix? 0, very good. So 0 matrix is a very good example. And so what would be a sufficient condition so you can do it? What? No? Invertible. Maybe. Here's an invertible matrix where you cannot do it. Okay, why can't you do it? Because if you want row sums and column sums to be 1, it's clear that, this is 1 and 0. This will have, after the scaling, will have to remain 1. So if you put, epsilon here, you have to put 1 minus epsilon here. 1 over epsilon here, right? And if you put delta here, you have to put 1 over delta here, right? So it will never be row sums and column sums 1 because this will never be 0. But actually, it's not so bad, this example, because you see that, the scale, after this scaling, you get something like epsilon delta here. So row sums and column sums are almost 1. So let's say we are relaxing this to almost mean arbitrarily close to, we allow it to be arbitrarily close to 1. So this will be 1, plus minus something tiny for anything tiny. And that's what we define as our target. And then for which matrices can we do it? Now this is okay. Right? But still, so that's invertible is not the right condition, and let me tell you what the right condition is. The right condition is that if you think of this matrix as a bipartite graph, then it has a perfect matching. So it's almost like invertible, but if the entries were indeterminate as opposed to zeros and ones. So that's what really counts. So the theorem of synchrone is that B is scalable only if the permanent of B is greater than 0. Okay? So permanent is just the permanent of B is like the determinant, the sum. So this thing is the sum of all permutations, and by a permutation of the product of BI of I. So it's just like determinant without the sign. It counts over all diagonals, sums the product of the elements in the diagonal. So it will be 1, it will be positive exactly if there is some diagonal in which all the elements are non-zero, are sort of positive. Okay? So this is a theorem, and I think...
So scalable means almost double stochastic?
Yeah.
Ah.
Yeah, double stochastic means that you can approach 1 as much as you want. Right. There is another characterization where you can get exactly 1, but we don't need it. So I have exactly 10 minutes. So let me tell you, I want to tell you the proof of this because it's so beautiful, and maybe you'll learn more than if I tell you how to use it. But let me just tell you roughly how it is used. So we want to be able to do this kind of trace calculation for the matrix M that we have. So we are going to scale M. So what we are going to do, so we have our M, and we are going to scale it. And let me point out something. Scaling does not change the rank, right? You just multiply, rows by constant, columns by constant. It doesn't matter. Change the rank. Without loss of generality, we can think of M, although it's not obvious why, but we can arrange it so it's to be. Okay, so let me say something. The permanent is positive. Is basically that it contains an identity matrix, or rather, it contains a non-zero diagonal. So it contains something like an identity matrix, but not with ones, but with some positive entries. It turns out that because of our condition, we can roughly think of our matrix, which is n by m, as after some appropriate changes, we can arrange it so m looks like something like a matrix which is k by n, in which all of these are non-zeros, all of these are non-zeros, and all of these are non-zeros. So it's as if you rearrange the rows, it contains contains k copies of the identity matrix on it, because you can take these guys. These are the non-zeros, right, in the matrix M. That's one identity matrix, and then there's this identity matrix. So it contains k copies of the identity matrix, which is exactly what you need, as it would be the condition to scale rectangular matrices. And the scaling will make it so that the row sums will be 1, let's say, and the column sums, because, well, the sum of row sums is the sum of column sums, always. And so this will be, the column sums will be k. So you can arrange it like this. It's not the sum of the entries we will apply to the square of the matrix, so it will be the sum of squares. But this is exactly what you want if you want to look at things like this. It will be just the inner product of vectors with themselves, or with columns with themselves, or with other vectors. So take my word for it. The scaling theorem, when it's generalized appropriately, will take our matrix M of non-zeros and will bring it to a situation where you can apply this. And that will put the rank lower bound. And that will be why you will lose this Q factor here, which you didn't lose if you just did this 0-1 calculation. That's where the number of elements per row come in. But anyway, this is one part I cannot afford to show you. I want to show you how to prove synchron 0. And the idea is really amazing. So what do? You have this matrix B, and you want the row sums and column sums to be 1. And you know that the permanent is positive. Okay. What can you do? So here's an idea. I mean, let's make the row sums be 1. Can we do it? Just forget the column sums for a second. How would you get the row sums to be 1? Yeah, you weight it by, so if the sum of the first row is, I don't know, S1, then you multiply it by 1 over S1. If the weight of the second row is S2, so you multiply it by 1 over S2. So you just multiply by 1 over the row sum. You get the row sum to be 1. That's great. So now this is 1. Okay, but of course there is no reason to think that all the column sums arrange themselves so nicely. So what can you do? Well, you look at the column sum here. Maybe it's C1. So you multiply by 1 over C1. You look at the column sum here, it's C2. You multiply by 1 over C2. 1 over C1. Very nice. So now all the column sums are 1.
You keep doing it many times.
Yes. So now it's some S prime. So just do it. And the claim is that this thing converges to a scaling if permanent. In fact, it's if and only. And I'll prove this to you in like 3 minutes. Okay? So this that's a claim. And I just want you to realize something that follows from this. Follows from some strengthening of it. 10 years ago, I wrote a paper with Nati Lineal and Alex Samorodnitsky on scaling for a different purpose, for deterministic approximation of permanent of matrices. And we observed that if you do a quantitative statement of the convergence, which I'm not going to do here, you realize that this process is the simplest, not necessarily the fastest, but it's the simplest to program algorithm for bipartite perfect matching. You want to know if a given n by n bipartite graph has a perfect matching or not. That's the same question as whether the permanent is positive. Well, just write its matrix, right? And start doing this, it's 2 lines of code. Normalize rows, normalize. Run it for n squared steps. Let's say when you finish, the columns are normalized. And check whether there's any entry here which is farther than 1 over n from 1. Okay? If it is, there is no matching. If it isn't, there is a matching. But otherwise it is. So it's the simplest. Yeah.
So is the best algorithm known?
It's the simplest.
Simplest.
No, its running time is it's more costly than the best known. Yeah, but in terms of
nicest.
code length, it's by far. Yeah, I don't know many algorithms that can be written in 2 lines. It's like the Floyd-Warshall algorithm. I think for transitive closure is one of my favorites. 3 lines, right? Because it's 3 loops. So this is two lines. Okay, so why does it work? Well, you know, it's clear that there has to be some Lyapunov function here, some progress. We have to be making progress, and the progress has to stop somewhere, and that's why we converge. So what would you pick as a progress measure? Which function along the matrices would you pick? I'll give you a hint, it's on the board. Nobody. Okay, so permanent is a progress measure. So first I claim that, well, after the first normalization we do, I claim that in this process, so we start with B, let's say B is B1, B2. So, and so on. That's the matrices we get in the sequence. First of all, I claim that permanent of BI is at most 1, because the permanent of a matrix is at most the product of the row sums. So it's at most 1. So at the other one end, it's at most 1. And I want to show you that it increases. Okay, that's why I want to prove that it increases. Okay, why does it increase? So suppose we move at one step here from B to B prime. Just in one step, from BI to BI plus 1, after another normalization. Okay. So what will it be? What will the permanent? I want to write the permanent of B prime in terms of the permanent of B. Well, what did we do? We multiplied, let's say the last thing we did was, the row operations. So when we multiply the rows by constant, how does the permanent change? The nice thing about the permanent, or the determinant, is that they pick exactly one entry from each row and each column. So whichever one of them we do, it just changes by the product of the weights. Right? So this will be the product 1 over SI, let's say the current row sums was SI times the permanent of P. Right? But does this expression ring a bell? What bell does it ring? Yeah, MG? Yeah. Yeah, maybe if I wrote 1 over n here, 1 over n here, and 1 over n here, it would ring the bell more loudly. So this is a geometric mean. A geometric mean is at most the arithmetic mean. So this has to be in the. So let me erase that, but it works also. But doesn't matter. Let me leave it. The geometric mean is at most the arithmetic mean, so that's at most. So it's in the 1 over sum of the SI and n sum of SI. 1 over n is the permanent of B. Okay, maybe I'm going in the reverse direction, maybe it's at least. So that's what I want to prove. Yeah, right? Everybody's happy, it's just that 1 over, just have 1 over the arithmetic geometry. But what is the sum of SI? If we are now doing the row sums, it means the column sums were all 1s, right? And the sum of row sums is the sum of column sums, so it's n. So this is 1. So this is bigger than this. Now that's not quite fine for convergence, right? I mean, just. However, I mean, you probably know well that arithmetic geometric inequality, if it's, the only place where it's tight is when all the elements are the same. And if they are not the same, then you get a quantitative advantage. So you can quantify how much you make progress if they are far from being equal. And that's enough to. Exactly.
Thank you very much. I will be very happy to answer questions in private. Thank you.